Hello, this is Maha, and I'm here with Raj on yet another episode of Share Trek HIV. And I welcome all our viewers for this new episode where we are going to talk today about Raj. I've been going through the comments, and some of the comments were tell us more about CAR T cells. So, what exactly is CAR T cells? Raj, please let us know. Our viewers, I'm sure, would be very curious to know what it is all about.
Yes, thanks, Maha, and thanks for facilitating these kind of videos because it helps a lot. And yeah, CAR T. So basically, I think what one has to understand about CAR T is basically it is the CD4 T cell which is modified and it becomes CAR T. So the question is, why do they modify it, and what is the difference between CD4 T cell and CAR T? So a CD4 T cell is taken from a patient with the blood, separated out of the blood, and then those CD4 T cells are genetically modified to express what is called as a chimeric antigen receptor. So imagine the CD4 T cell to be like a sphere, and a chimeric antigen receptor is a kind of a tentacle coming out from there. And that chimeric antigen receptor basically is tuned so that it can adhere to a particular antigen. And when it adheres to an antigen, then the CD4 T cell will release what is called as cytokines. Think of them as cell poison. So that cell poison will kill the cell that has got the antigen. So this is how CD4 T cell is modified to become CAR T cells. So CAR T stands for chimeric antigen receptor T cells.
Okay.
So
So
that's
I've
how
been
it works.
hearing this antigen again and again. So what exactly is an antigen?
So the success of CAR T cell happened with blood cancers. So
Oh,
in blood cancer, what happens is that the blood cell becomes cancerous. When a cell becomes cancerous, it means that a normal cell has started growing abnormally, and therefore it is cancerous. And it's not performing its normal functions, and it's creating problems in the body. So when blood cancer cell is there, when a blood cell gets cancerous, then it exhibits some proteins on its surface. So scientists work very hard to find out how do we identify a blood cell as being cancerous, because there are so many blood cells. How can you say this one has cancer and that one doesn't have cancer? So they took a lot of blood cells, healthy cells and cancerous cells, and tried to find what is common among cancerous cells and what is different about normal cells. And then they found that there were some differences. They were basically surface proteins. And then they
oh.
started studying to find out for different types of blood cancer, what are the kind of proteins that are there on surface of those kind of cancer cells. And then they identified some proteins called CD19, which was a protein that they identified. CD40 is another protein they identified. So using those proteins, they could identify that a particular blood cell has got cancer. So what they did was they took the blood from the patient, and one of the cells in your blood is the CD4 T cell. So they separated the CD4 T cell, and then they put some genetic material into it so that the CD4 T cell can express a chimeric antigen receptor, which would go for the antigen called CD19 or CD40, depending on which therapy they are working on. In this example, I'll assume CD19. So once the cell was created from the patient's own blood and it was put back into the patient's body with this chimeric antigen receptor, which is looking for CD19, the patient's immune system, which consists of natural killer cells, saw those CD4 T cells and found nothing wrong with them because it was the patient's own CD4 T cells. So these CD4 T cells were able to go and latch on to CD19 on blood cancer cells and kill those blood cancer cells, because as soon as they would latch onto the blood cancer cell, the CD4 T cells will release cytokines, and that would cause CD8 T cells and natural killer cells and others to kill the blood cancer, or they would release cytokines to kill the blood cancer cell in which they were attached.
You know
So
what? When you're explaining these things, I can actually visualize what's happening inside the body. I
That's the
mean,
idea.
this is beautifully explained.
Yeah.
So
So
where exactly is this? Yeah, please continue.
yeah, so this is what CAR T cells are famous for. And there were half a dozen therapies for blood cancer using CAR T cells that were approved by FDA. And they were selling for very huge amounts of money. And it was wildly successful. So scientists thought if we can do CAR T for cancers, blood cancers, then we should be able to do it for solid tumors, for lupus, and also for other kind of diseases. And that's where I think you are alluding to our viewers' comments regarding CAR T for HIV. So that's the comment you're talking about, right?
Yes, yes.
Yeah. So I
And
would like to, yeah, go ahead, please. Yeah.
where exactly is this research happening?
Oh, okay.
Who is
Yeah.
actually doing all of this?
Right. That's a very good question. So I'll share a screen with you to show you where it is happening. So are you able to see my screen?
Yeah. Okay. Yes, now
Yeah.
I can.
Yeah. So in this screen, you will see institution called UC Davis Health. So UC Davis Health announced on March 24, 2022, that they are investigating whether CAR T cells offer hope for an HIV cure. So all that they are saying here is that um, for this study, we will educate the cells by inserting a gene to target cells that have been infected by the HIV virus. And the idea is these modified cells will attach to HIV infected cells and destroy the cells that are infected while also stopping the infected cells' ability to replicate. So basically, what they are doing is they are not sending this onto HIV virus.
Hmm.
They are sending it on to CD4 T cells that are infected with HIV.
Correct.
Right? So how are they able to do that is a question for which I don't have answer. We'll have
Hmm.
to get more detail from them. Right?
Hmm.
So this was on 24th of March 2022. And
Hmm.
these things take time because you have to get grant money and all that. Then in April 19, 2023, they announced that clinical trial begins using CAR T cells to potentially cure HIV.
Hmm.
So they expanded upon that. They have not yet given information on how exactly it works, but they spoke about, recruiting patients, and around 18 patients will be studied. Cohort 1, cohort 2, cohort 3. They're talking about dividing those 18 into groups of 9 each. So there'll be 3 groups, different doses for them, and then to see how it's going to work. So they are deriving this idea based on successful treatment of cancer. Okay. So that's what they are trying to do. There is no new
But with
information.
regard to cancer and it is a very breakthrough kind of a treatment, right? I mean, I didn't
Yes,
know
it's
there's
a
such a
it's a breakthrough
treatment
kind of treatment, but
existed.
I would also like to give some caution to our viewers because
Hmm.
I'm not wanting to discourage anybody, but I want to say that the human body is very, very complicated. It has got checks and counter checks and counterbalances. So one has to be cautiously optimistic about everything. I'm cautiously optimistic about CAR T. Take the case of CAR T for curing blood cancers, right? The two kinds of therapies worked. CD19 specific CAR T therapy and CD40 specific CAR T therapy, they have been used and they have worked successfully for many people. But the FDA recently put what is called as a black label warning, black box label warning. And what that basically means that any future patient who's going to take this therapy will have to know that there's a risk of cancer over and above what they already have. Because what FDA found was in extremely rare cases, they found instances of mutated CAR T.
Oh,
So that's the problem. And now there's a allogenic CAR T for cancer for CD19 being developed by a company called as CRISPR Therapeutics, which is in phase 1 clinical trial advanced stage. They're doing very well. But that's an allogenic CAR T therapy. What we have in the market is called as the autologous CAR T therapy because it's the patient's own blood that is taken. And from there, they take out the patient's own CD4 T cells, modify, and put it back in the body so that the body's immune system does not kill the modified CAR T cells. Whereas the problem in that approach is that even though the immune system doesn't kill it, that is a positive, the negative part is two things. One is the patient is already weak from cancer. So their
Right.
CAR T cells are less potent, and also the CAR T cells are likely to be less stable. So when the CAR T cells are less potent, then they are not as effective as they could have been if they were healthy CAR T cells. And the second thing is that because the patient's blood itself shows blood cells which are not stable and have become cancerous, the chance of the CAR T cell also getting malignancy is higher. So as a result, you may have rare cases where you have malignant CAR T cells. And the malignant CAR T cells means the therapy itself developed cancer, right?
Oh, yes.
So that's a very, very rare instance, but that black box warning has come. Now, the challenge for allogenic therapies is that even though they are coming from healthy patients and are likely to be very potent, and the fact that the patient can get it immediately when the doctor says you need CAR T therapy, they can immediately get it off the shelf because a healthy donor has already given it. All the processing is done and it's sitting in the shelf waiting to be deployed. Whereas in autologous, it takes around 6 or 7 weeks to take the blood, extract
Oh,
CD4
that's
T
the
cells,
whole process.
modify them, then do quality control, and then multiply the CD4 cells to sufficient quantity so that you can inject it back into the body. All that is already done in allogenic. It comes from a healthy patient, healthy person, and then that is put into the patient's body. Now, the biggest challenge for allogenic is evading the human immune system, which consists of natural killer cells, which consists of the body's own CD4 T cells, and other components of immune system. So allogenic therapies generally devise extra modification to the CD4 T cell so that it can be invisible to the natural killer cells and other CD4 T cells. And they do that by removing some surface proteins on the CD4 T cell so that it is invisible to the NK cells receptors and others. NK cell stands for natural killer cells.
Natural killers.
Yeah, so that
Okay.
way allogenic therapy can work. So that is the cautionary tale in cancer. Now,
Mhm.
let us shift off to what UC Davis is doing. UC Davis is apparently trying to look for markers on the CD4 T cell so that the CD4 T cell modified CAR T therapy can go and latch onto infected HIV cells and then recruit natural killer cells to come and kill them, or
Okay.
recruit CD8 plus cells to come and kill them, or the CD4 itself releases perforin and tries to kill the CDT cell. Something of that sort is what I think they are attempting. Now, if you look at AGT 103-T, what it has done is it has given a cloak around the CD4 T cell, which is modified, and its CCR5 receptor is taken off so that when it comes in contact with HIV, HIV cannot enter it, but CD4 T cell can continue doing its work of releasing cytokines, recruiting CD8 plus T cells, etc., to kill it. So I'll say the closest we have to some strategy like this right now in an advanced stage is AGT 103-T,
AGT.
even though it's not a CAR T cell, it's a modified T cell, which does not have a chimeric antigen T cell receptor, but it has got a CCR5, which has been down-regulated so that it's not expressed on the surface. So HIV cannot get into it through CXCR5. So, sorry, CCR5. So that's what has been done. But coming back to this CAR T cell, right? The CAR T cell, which is modified to go and kill this HIV infected CD4 T cells, I hope they disable the CCR5 in those CAR T cells, or else what is likely to happen, in my opinion, of course, I'm not a scientist, so I will say that I could be totally wrong. Scientists know more than I do. But when these CAR T cells go and latch onto this uh, infected CD4 T cells, the infected cells are actually in the process of releasing new HIV particles. So those new HIV particles could infect these CD4 cells using the CXCR5 and the CD4 receptor in order to infect them. Now, if introducing chimeric antigen receptor to a CD4 T cell involves taking off the CD4 receptor, then I would say that the strategy would be successful, right? Because if there is no CD4 receptor, then HIV virus cannot get into the CXCR and into the CD4 T cell, so it will be safe. So I'm hoping that they do something like that. But in my opinion, the best bet is to use NK cells or natural killer cells with similar modifications. Natural killer cells, if they can be given this chimeric antigen receptor, which can target surface proteins on HIV, then natural killer cells do not have CD4 receptors, even though they have CCR5 and CXCR4 receptor, both of which are used by HIV virus. But HIV will never be able to expose the GP41, which is what is needed in order to push everything into the CD4 T cell and infect. So NK cell can be doing a great job in this position. So I would actually anxiously look forward to um, potential NK cell related HIV therapies. So that's how I would
Okay.
answer that.
Any known side effects for this particular?
Right. So in the early days, when they did CAR T cell therapy for cancer, one of the side effects they were talking about was high cytokine levels in the body, and cytokine levels cause inflammation. So that's what was spoken about in the early days. But scientists have found out ways of managing cytokine toxicity and all that stuff. So I don't see any side effects as such with this CAR T therapy approach. So
Mhm.
yeah, I don't see any side effects, but we'll have to wait and see what happens because clinical trials are exactly for that purpose. So when I talk
Mhm.
about side effects, I would like to differentiate between immune response from the body and side effects. When I talk about immune response, I'm talking about the body's immune system fighting against the therapy. So that will be taken care of in phase 1 trial where they see whether any problem happens to the patient, whether the therapy can sustain in the body. All those things are in phase 1. When we talk about side effects, it's totally different. Side effects means after getting this therapy, whatever reaction that the therapy does in the body, does it cause high blood pressure? Does it cause vision loss? Does it cause diabetes? Or does it cause, inflammation in the joints? Those are all side effects I would talk about because they are the result of the therapy working in the body and causing other problems. Those are the
So
side.
some those side effects are something which are very obvious, which would be very immediate also. If correct
Yeah.
me if I'm wrong.
I would say that side effects, I would say that immune response could be immediate, but side effects may or may not be immediate. Side effects may take time to build up and then
Could we say they are more
manifest.
obvious? They'll come as an obvious thing.
Yes,
Some
people will start feeling it. I mean, I don't, the way I differentiate between immune response and side effects is that immune response is your immune system fighting against your therapy, right?
correct.
Whereas side effect has got nothing to do with your body fighting the therapy. The body is saying, okay, you go and do your work, you do your therapy. So the therapy goes and it does something and releases some chemicals and whatever in the body, all natural, which comes up in the body. And as a result of that, the environment in the body is changed. And because of that, maybe the pancreas are getting a signal that do not release too much of insulin. And therefore, you're having blood sugar regulating problems. So this
True.
is a side effect. This is not the immune system doing it, but it is the effect of what the therapy has done
Mm,
in the process of solving the original problem. And that
correct.
has released some proteins or that has released some byproducts into the blood, which has sent a signal to the pancreas, for example, to say, send less insulin. Or it has sent a signal to the body to release some proteins, which makes your eyesight go a bit fuzzy.
Um,
So it can happen immediately or it could take 3 or 4 months to manifest. So it all depends on what it is, right? So one can't say, and these are all exactly the things that the clinical trials try to capture to make sure that nothing in the system, in the human body is disturbed because of a therapy. So
so
this,
like you said, there were at least 18 people in the clinical trials, right? And they were
yes,
divided into the first,
yes.
three, whatever.
Yes.
divided into 9 each or something like that.
Yes.
So, but
Three groups of 9 each, and each group
yeah.
had different doses, and then they will see how it works. And I think again here we have the problem of dormant cells. We have the problem of macrophages and dendritic cells, which contain HIV. So how are we going to address those? That is the question. So I'm going to reach out to UC Davis and try to find out if we
I
can
was
get,
just about to ask you that.
yeah, to get them to join us so that I can ask some of the really good questions that you asked me for which I didn't have answers. I could ask them and they could explain to us exactly how their CAR T works. And yeah, that would be helpful. So let us see.
So, any other thing that any, you know, positive that you see about this therapy, which could really in the future work out for us?
Yeah, so the way the CD4 T cells work in our body is that as long as the CD4 T cells are in use, the body will let it survive. But if it is not in use for a certain period of time, then the body recycles those CD4 T cells. So what happens is that for recycling the CD4 T cells, the CD4 surface proteins are expressed, MHC proteins are expressed. So what happens with HIV is that it keeps the HIV CD4 T cells alive for a longer period of time by using the NEF protein, which it has got a NEF gene. HIV has got NEF gene, which creates NEF protein. And the NEF protein downregulates MHC1 and upregulates MHC1. And MHC1, when it is on the surface of the cell, attracts natural killer cells to come and kill it. So when a cell is in distress, when a cell is infected, it sends up a protein called MHC1. And MHC1 is the message to natural killer cells saying, listen, I'm infected, kill me, right? So natural killer will come there, get latched to it, release cytokines and kill it. So HIV, because it has got the NEF protein, is able to hide HIV infected cells from natural killer cells.
Okay.
So yeah, so the positive, coming back to the positive, is that if we were able to engineer a CAR T cell, which is constantly hunting for HIV, it will multiply itself and the activity will keep on going on as long as there is HIV in the body. And I suppose that if you want to do the other natural killer cell therapy that I was talking about, then you would have to come up with some way of either making the natural killer cell target CD4 T cells with low MHC1 or no MHC1 so that you can target all the infected HIV cells, or you find a way to create a medicine that can go into CD4 T cells and counteract NEF so that NEF is not active and MHC2 protein is promoted to the surface, and natural killer cell will automatically come and kill that HIV cell without getting infected because it doesn't have CD4 receptors, right?
So it was wonderful talking to you today, Raj. Do you have something? I thought you were going to say something.
No, so the good thing is that if these kind of therapies succeed, NK cell or CD4 CAR T cell therapy, then they will persist in the body for a long period of time. As long as there is HIV in the body, they will still be there to fight it. And once HIV is gone from the body, maybe 6 months or 1 year after that, I think they will potentially lose those cells, but they won't need it in their body. So you have these things like for tetanus, we have booster vaccines. All they do is that the CD4 T cells which are activated and the B cells which are activated to the tetanus antigen, they have not encountered tetanus in the body for a long period of time. So 2 years or 3 years. So the body says, oh, you know what? I can use this CD4 T cell for something else. So let me recycle them. So those things are gone. That's why you take a fresh tetanus shot, which releases those antibodies, and then new CD4 T cells get sensitized to it, and then memory remains for another 2 or 3 years until you need to have a booster. So these HIV CAR T therapy will continue to work in the body as long as HIV is in the body and keep on
But
hitting it.
how would you know that? I mean, okay, you have to keep doing those tests again and again, find
CD4
out
count test you have to do.
count and all that. Yeah.
Yes, yes,
So,
yeah,
great.
yeah.
So, Raj, it was wonderful talking
Thank
about
you.
this therapy, and I really feel that this has some kind of a hope. The way you explained it, both the autologous and the allogenic and all those things. I mean, there is some hope I feel in this area, and
Yes,
I think things would get much clearer once you talk to UC Davies.
yes.
I'm looking forward to that interview actually.
Yes,
So
hopefully they give us the interview and we get to talk to them. Then we can find out the method by which the CAR T works, and it's quite possible that they have introduced the CAR T in place of and also probably muted the CCR5, and it must be a strong solution.
I'm
So
sure they've reached somewhere in the
these
therapy,
are all
somewhere.
brilliant scientists. You know what?
Yes, absolutely.
We are just book warriors. We read paper here and there, and then we make our assumptions. I mean, I don't have a science background, so I'm a fine one to talk
But
about it.
but we
But
are warriors nonetheless, not to be
yeah,
forgotten.
yeah, because our audience is so keen. We have audience from the villages, people who don't speak
Absolutely.
English, and then we have audience who are highly educated in their respective fields, but not in science, like in medical science. They're aware of what is happening to their bodies. They want to know more about it, and we are kind of producing a bridge between publications that talk about what is being done. So
And
our
even
knowledge
among
is
our, yeah, I feel, Raj, even among our viewers, there are a lot of book warriors. I can see the comments and I know that they've been reading up a lot.
yes, reading is very
So,
important. So what we are doing is, in our small way, we are reading whatever we could, trying to make sure our information is as clear as possible. But if I get a chance to talk to the scientists at UC Davis, they will be opening our eyes to so many things, because there are so many things we don't know about CD4 T cell, about NK cell, about HIV, that these scientists know because they're in the weeds of these things. So we are operating at a very high level of information. They are operating at very nuclear level or molecular level. So
correct.
let's hope for an interview.
Thank you so much, Raj. It's been wonderful hearing about CAR T cells today and the in-depth information that you gave about everything to us. Really invaluable. And I hope our viewers would have loved this episode too, as much as I did. And thank you, Raj. Until our next episode, then it's bye from me and Raj. Thank you so much for watching us.